Good morning. Welcome to Monday. It's here. It's here. It's going to be great. It's week 11, right? Week 11? Week 12? Week 11? Good morning, Joey. Is that an O or a 0 that's capitalized? Or that's big in your name? Morning, other Joe, a 0, I think. Isn't that great? In MATLAB, there are some variables that, shouldn't be used. O is one of them. L, because O looks like a 0, 0 looks like an O. L looks like a 1, 1 looks like an L. That's a really bad one to debug. Yeah, sometimes letters and numbers are fun. Ah, I see. That makes sense. Usernames in the future are going to be so obscure. Like, everybody's taking normal usernames. Well, you've got a 20 attached to your name, so that kind of helps. Unless there were, 19 others. Yeah, usernames are lame. Okay, I gotta flip my computer around. I hate making passwords. Passwords are annoying, but thankfully we have things called password managers these days. My dad would write down all of the passwords that he had on index cards in his office. He'd just have a index card. Ooh, for Discord, just J.R. Conrad. All the cool usernames. I have my last midterm of the semester. Wow, that's awesome. So does that mean you have 3-4 weeks of relaxing time, or do you have projects instead? Man, I feel like you've had a midterm every week since I don't know, week 6. Do you have projects? So do you guys have projects in lots of your classes or mostly just exams? I don't know, as freshmen and sophomores, I imagine mostly just exams? Oh, 202, that's right. I forgot 202. Okay. Matt, I understand. I had that last semester. This semester's a little bit easier for me, thankfully. But last semester, I felt like I had no days off. It was a lot. Thanksgiving break was awesome. However, I did not want to come back from Thanksgiving break. This semester, I don't know. I like the fact that there's linear algebra, that we kind of switch. It kind of shifts the mindset of okay, I'm learning something different now. I mean, you still have your project, but this class at least has a natural transition point, which personally I think it helps my mentality. Granted, I don't have 4 other classes to deal with this semester, but I'm hoping that helped to some extent, or that's helping to some extent. Projects and papers. I hate papers so much. I can write, I can communicate, but writing a paper is the worst thing for me. A 3-page paper would take me a whole week to write. 3 pages, that's really it. So I hate writing. It's the worst. So I'm sorry that you guys have papers. And I'm sorry you have to write for this project too, but it's good to practice to learn communication. Linear algebra is way less satisfying when you get it to work out because you have all these numbers crossed out. I know. Linear algebra is different. It's different. There's a lot. And frankly, this isn't a linear algebra. This isn't a linear algebra class, which means we're not going into why we do these numbers, and even I don't understand everything that's happening behind the scenes with linear algebra. I'm much more an applications person. Like, okay, tell me how to do these calculations. I am not a mathematician, so I don't know exactly everything that's happening when we do these calculations in linear algebra. Speaking of which, let's transition to our content today. I know, I completely understand. It's so frustrating. There's so many, so I read through you guys' quizzes responses, and a lot of you guys mentioned that, well, half of you guys were talking about the content for this week, which the videos that you watch on Friday, or in this case, one video, I recorded it 3 times because my mic was muted twice. So you just had one video because I got frustrated, and I was like, I'm condensing this as much as I can. So you had one video. Those videos are not supposed to be all-encompassing. You're not supposed to be able to know everything from those videos. They're supposed to introduce you to the concepts that we are going to go through with our examples in class on Twitch. So you guys can stop at saying, I don't understand how to do determinants, I don't understand what this means, because you're not supposed to, necessarily. You're not supposed to understand everything. It's supposed to be an introduction to the ideas that we go into apply in class. And the other half of you guys talked about how Gauss elimination and Gauss-Jordan elimination, they're long problems. They are so long. It is annoying, it is frustrating, and I understand. I put together 4x4 examples last week, and that 4x4 example for Gauss-Jordan elimination took me probably like 2 hours to type up because I kept making mistakes, I kept formatting things wrong, but it just took forever, and I understand that. However, those concepts are very important for you guys to understand because they're going to be central to many of the weeks in linear algebra. So they're going to show up all the time. So it's not so much that things take forever, but you need to practice row operations. You need to understand how to do them and what we're doing with these problems. So I just wanted to go through or show you some of the examples that we do have put together. So there's these PDFs on UB Learns for you guys to look at that go through more examples. So there's video examples that I created from last year. There's some from lecture. There's these written examples. So you should have lots of examples to use for studying, for practicing, all that fun stuff. But given a system of equations, we are trying to solve for our unknowns. We're trying to solve for x, y, and z. And traditionally, you would probably use substitution for this, or you would use some form of elimination with the equations themselves. When we do Gauss elimination, we are essentially doing a algorithmic, a consistent way of doing elimination, using the same mentality. It's kind of like giving you like a recipe for how to solve this using elimination, where you add your equations together and you remove an unknown. So what we do is we write our system in what's called the augmented matrix form, where over here we have our A matrix, so our coefficients and equations. So equation 1, equation 2, equation 3, unknown 1, unknown 2, unknown 3. Doesn't matter what our unknowns are called. And then over on this side we have our B vector, our constants from our right-hand side. And then what we're doing is we are performing elimination, where we are trying to get it so we can eliminate 2 of our unknowns in one equation, eliminate 1 of our unknowns in another equation, so that we can easily solve our system. So here's stepping through all of the basics. This example kind of goes through it more, I'll zoom in for you guys, goes through it a little bit more outlined, where we can see that I want to make this one a 0, this 2 a 0, and I'm going to do that using this one. I could have done this row as well. I like to use row 1 to eliminate my zeros in column 1. So I'm multiplying this one by -2. When I do that, I end up with this matrix over here. Now these two numbers are the same and opposite, so I can add them together. What that's going to do is that's going to create a 0. If you do that in this column, though, you need to do it across the entire row. So it's -2 plus 2, which is 0. 12 plus -10, which is 2. 8 plus -9, which is -1. 10 plus -4, which is 6. Once I have a 0 there, I want to try to get a 0 down here. Before I do that, though, I'm going to divide row 1 by -2 again, just to make it down to 1. You don't have to do that. And then I'm going to take this row and add it to this row. So 1 plus -1 gives me a 0, -6 plus 6 gives me a 0, -4 plus 5 gives me a 1, -5 plus 3 gives me a 2. And I've got my lower triangle of zeros. Once I do that, I can use back substitution. Write my system of equations with my new augmented matrix. Gauss-Jordan and Gauss elimination can be used with any system of equations. So if you look at this equation, or this system, notice we have 3 equations and 4 unknowns, x1, x2, x3, x4. If you ever run into this situation, you're still going to do the same process. You're still going to find that lower triangle of zeros. You still want to find this 0 first, and then this 0, then this 0, and then you want to get this one into a 0. That is always your steps. You're trying to find that lower triangle of zeros. Anything else that happens out here is just icing on the cake. Either it works for you or it doesn't. In this situation, though, when we get our lower triangle of zeros, our system of equations, when we write it out, we can't solve for all of them because we don't have a 4th equation. You need 4 equations to solve for 4 unknowns. But what we're going to do is we're going to find our system in terms of our other unknowns. So we're going to solve for x4, or we're just going to have x4. It's an arbitrary parameter. x4, given if we know what x4 is, here's our equation to get x3. Here's our equation to get x2. Here's our equation to get x1. So there's an infinite number of solutions here. Any value for x4 would work. Given x4, we can solve for x3, x2, x1. So Gauss elimination and Gauss-Jordan elimination, as we'll see in a minute, can work for any size system of equations. That's not always the case for all of our methods, but we're still always trying to find our lower triangle of zeros. That is our goal. And we will learn more about this notation in 2 weeks? Yeah, 2 weeks. Next week is LU factorization, woohoo, which is more row operations. And PLU factorization, which is more row operations. Fun stuff. And then after that, we'll get into this notation. Okay, but for this one, we can still use Gauss elimination. We just end up with an infinite number of solutions, where we just have our arbitrary parameter x4. We just say it's anything you want it to be. Given x4, then we can solve for x3, x2, and x1. And there's another 3x3. What's in this one? Okay, so you might always also run into a situation where you end up with all zeros. So if you ever end up with all zeros on just the A side of your matrix, then that means that you don't have a solution. So when you write this last equation, you end up with 0x plus 0y plus 0z equals -2. That doesn't make sense. You can't have 0 equals a number. That's not how it works. So this is an instance where this has no solution. So still the key is you end up with your lower triangle of zeros. This 0 just happened. It just appeared as you were doing your row operations. So just get your lower triangle of zeros, and then you can write your system of equations and solve for everything after you get that. And here's the wonderful 4x4 solution, 4x4 system that I put together. Okay, same thing for Gauss-Jordan elimination. Notice this, there's not very many unknowns in this system, which is great. That just means there's lots of zeros that show up in your augmented matrix. Notice there's 3 equations for unknowns. That doesn't matter though. With Gauss-Jordan elimination, we just make this as close to identity as possible. So start by making this a 0. Well, actually, I rearranged these once again. You can rearrange rows. It's not always beneficial. Sometimes it makes you go in circles, but here I rearranged rows as an example. And then I got 0 here, 0 here, kept working my way through. Notice this furthermost part looks like identity, but I have these here. Once you get this, just write your system of equations. x3 minus 3x4, 3/4 x4 equals 0. So once again, here's an example where x4 is just arbitrary. We don't really know what it's going to be. It can be anything. We have an infinite number of solutions. But your goal for Gauss-Jordan elimination is get this side to look as close to identity as possible. And then just write your system of equations at the end. Write whatever this ends up being. Here's a number 3x3 example. Lots of more row operations with Gauss elimination or Gauss-Jordan elimination. This looks like identity. Here we can easily see what our system ends up being. x1 is -1, x2 is 3, x3 is 2. And then, okay, here's my 4x4. Here's the 4x4. That took forever, mostly because I messed up like on a row operation here. I made that the wrong number or something. It was ridiculous. I think it was one of these 6s. I think I made this a 12 or something. It was annoying. So yes, these problems are long. They are annoying because there's so many small places where you can make a mistake. It is very frustrating. The practice is important. They do take forever though. Okay. But for this problem, start by making zeros in your column 1. You can always do that using row 1. Then make zeros in your column 2. You can always use that. Do that using row 2. Make zeros in column 3. You can always do that using row 3. And then make your zeros in column 4, or however many more you have. You can always do that using row 4. And you keep working your way through until you get identity, and then you can see your solution. X is -2, Y is 3, Z is -1, W is -2. It doesn't matter what your unknowns are called. It's just your first unknown, second unknown, third unknown, fourth unknown. Yeah, just make sure your letters match whatever is in the system. Okay, so I wanted to go over some of that, some review. On the final, it will probably, so on the final, if you do have something this long, it will be whole numbers and there will be more zeros. It would probably look something more like this, where there's lots of zeros involved already. I will have more information on that. Oh crap, the drop deadline's on Friday. I have more information than on Tuesday or on Thursday, but I'm not going to see you guys before then. We are mindful about, or at least I try to be mindful about how much writing there is on the final. So you will not have to solve a 4x4. You will not have to solve something like this from scratch. There will be some mechanism involved. We might say, especially for this final, since you'll have access to UB Learns, we might say something along the lines of use MATLAB in order to get the solution, and then you're going to need that solution to solve for something else. But in general, I try to be very, very mindful about how much writing there is on the exam and how much time it takes. In general, though, the final does tend to be lengthy. You'll have 2 hours probably again to do it. But it does tend to be lengthy because there's a lot of writing in these problems. There really is. You guys know that. You'll see it as you practice. Okay. So that's just some information, some final information from last week's material. Key thing, Gauss elimination, get that lower triangle of zeros. That's your goal. Everything else that appears is fine. Not a problem. It's just how you interpret that final result. Same thing with Gauss-Jordan elimination. Get that to look as close to identity as possible. Whatever else, however it appears at the end, that's how you interpret it. It's how you interpret it. Okay. So, this week, we are going to be talking about determinants. Like I said, your video this week was one video, 7 minutes long. But I introduced this idea of determinants and inverse, which we've already seen. We've seen this with a 2x2. We were introduced to the ideas and the concepts back in week 4. But we're going to be calculating determinants a lot this week. Which is fine. I find this material a little bit easier to digest, a little bit easier to debug and figure out. So it's kind of a refreshing break from row operations. But yeah, I don't know. It's just calculating determinants. So, like I said at the beginning, we're really not going to go into what is a determinant or why we calculate determinants. It has to do with a three-dimensional space. Essentially, a determinant is a volume. Once again, not really going to go into that. We're going to go into how to calculate it. So, for any matrix, a determinant can be calculated using something called cofactor expansion. So we're going to talk about these cofactors quite a bit. And I didn't go into this in the video because this essentially is where we are going to be living in this space in terms of our application, in terms of our examples. So before I get into that, let's review a 2x2. So if I have a 2x2, my determinant, I draw my little fish. It's going to be my AD minus BC. So AD minus BC. So it's going to be 3 times 5 minus 4 times negative 4. In this instance, it's 15 minus negative 16, or 15 plus 16, or 31. So my determinant of this A matrix is 31. So here's our determinant notation. The single bars, this is determinant. The double bars is norm or length. That's where you have the square root of all the elements squared. Single bars for a scalar value means absolute value. For a matrix, it's determinant. Okay, so just just remember that notation. Single bars, determinant, double bars, norm, or length. Okay, that's for a 2x2. For a 3x3, there's a couple ways we can find the determinant, but we are going to start by talking about cofactor expansion. So a cofactor of a matrix is just the determinant of a submatrix. So essentially, a cofactor exists for every single element in A. The way you find a cofactor is you're going to remove a row, remove a column, and find a determinant of what's left over. So we have some steps in our notes. Finding the cofactor of an element in a matrix. That's a little too big. First, we are going to remove the row and column that the element is located in, and then calculate the determinant from the remaining values, and then adjust the sign. Whoop. And then adjust the sign. The sign is adjusted according to this grid. It just starts at the plus in the upper left and then alternates moving forward and down. Okay, there we go. So, if I zoom in on this matrix, I have a cofactor for every single element in this matrix. So the cofactor for this one, the cofactor for the 1, 1 location looks like this. I'm going to remove the row and remove the column it's in and find the determinant of my remaining elements. So my remaining elements are 5, 5, 5, 5. So it's going to be 5, 5, 5, 5. 5 times 5 minus 5 times 5, or 0. Then I need to adjust the sign. The sign for a 3x3, I adjust it according to this. I draw a plus in the upper left, and then alternate. Come on. Go down. Come on. There we go. So in the 1, 1 location, my sign is a plus. So it's a positive 0. Okay, I did it. I found a cofactor. Woohoo! Let's say I want to find the cofactor for this number. Cofactor for the 1, 2 location. I remove the row and column it's in. My determinant is going to be composed of -4, -2, 5, and 5. Or -4 times 5 minus -2 times 5. -20 plus 10, or -10. I'm going to adjust the sign based on this number here. So a negative, so it's going to become a positive 10, or a -10. There we go. I found the cofactor for 1, 2. If I want to find the cofactor for this one, cofactor for 1, 3, I remove the row and column it's in. And then I do my determinant of the remaining numbers, -4, -2, 5, and 5. So -4 times 5 minus -2 times 5. It's going to be -10. It's the same one as above. And here's how I adjust the sign, my plus. So it's going to remain a -10. If I wanted to find the cofactor for this element, cofactor for 3, 2, row 3, column 2, I remove the row and column it's in. My remaining elements, 1, -4, -4, 5. 1 times 5 minus -4 times -4 equals 5 plus 16. Nope. Minus 16, -11. My sign for right here is a negative. So I make it my negative, so it becomes a positive 11. That's how you find your cofactors. You find whatever element you're finding the cofactor for, pick a number, remove the row and column it's in, find your determinant with the remaining elements, and then adjust the sign as according to your grid. If this was a 4x4, the grid would just keep going. It just alternates. You always start with a plus, and then you alternate going in any direction. Okay, so why? So why do we need cofactors? To be honest, I don't know what a cofactor means physically. It's a determinant, so it's another volume. Cofactor is also the version of a minor. But these cofactors show up in linear algebra, specifically when we're calculating determinants, when we're solving systems using Cramer's rule. So these cofactors show up repeatedly. Okay? So we will see them a couple times. See them when calculating determinants, see them when finding the inverse of a matrix, and see them when we do Cramer's rule, which is just more determinants. Okay, so any determinant can be calculated using what's called cofactor expansion. So let me go back to my notes and look at those steps. So finding the determinant using cofactor expansion. Okay, what we're going to do is we're going to pick a row. So we're going to choose a row, and it turns out we can choose a column as well. We're going to choose a row or column, pick one. For each element in that row or column, we are going to find all the cofactors. And then what we're going to do is we're going to multiply those cofactors by the element in the row and add them together. Generally, in order to aid in this process, we choose the row with the most zeros. So let's look at an example of this. Let's go back to our wonderful determinant, our wonderful matrix. Okay, so I have this matrix here, and I want to find my determinant for this matrix. So first I'm going to pick a row or a column. I'm going to pick row 1. I'm going to pick this row. Okay, so I've highlighted it just to indicate we're picking that row. Then I'm going to find the cofactor for every single element in that row. So for this number, it was positive 0. For this number, it was positive 10. And for this number, it was negative 10. Okay, so I've done that. That's great. Woo. So my last step my last step is I'm going to take these numbers in my row, multiply them by their corresponding cofactor, and add them all together. So I'm going to take 1 times its cofactor here, which is 0. So this 1 plus 0, plus this 1 times its cofactor, which was positive 10, plus this number, negative 4, times its cofactor, which was negative 10. Or 0 plus 10 plus 40. Or my determinant of A equals 50. There we go. I did it. I found my determinant for something bigger than 2 by 2. Woohoo! That's it. And it turns out this process works for any row or any column. Let's do it with column 2. Let's do the same thing with column 2. So how about I copy that, paste it over here. There we go. So let's do it for column 2. So I'm picking column 2. So for this 1, 1, or this 1, 2 location, my cofactor was positive 10. I already did that one. I don't want to do it again. Why repeat something? Okay, now for this 5 here, I'm going to remove the row and column it's in. So column, or cofactor 2, 2, row and column. My determinant is going to be composed of 1, negative 2, negative 4, and 5, or 5 minus 8, or negative 3. My sign there, plus, minus, is a plus, so I leave it. So my cofactor is a negative 3. Okay, my last element, this one, cofactor 3, 2. Remove the row and column it's in. Hey, I already did this one too. It was a plus of 11, but we'll do it again. Remove the row and column it's in. 1, negative 4, 5, my remaining elements. So it's 5 minus 16, or negative 11. I adjust my sign, which is a negative, so it becomes positive 11. Okay, I picked a row, or I picked a column in this instance. I found all my cofactors. So now I'm going to take the elements in my row, multiply them by the corresponding cofactor. So it's 1, so determinant of A is 1 times 10, 1 times 10, plus 5 times negative 3, plus 5 times positive 11. Okay, we should get the same answer. If I did my math right, we should get the same answer as we got before, which was 50. So here I have 10 minus 15 plus 55. Or negative 5 plus 55, or 50. We did it! It's mildly satisfying, right? Although typically you'll have to calculate determinant once. Okay, so that's cofactor expansion. That's finding the determinant using cofactor expansion. You pick a row or a column. You can choose any row or any column. So if we look at this one here, this 4x4, this process holds for any size matrix. Any size matrix. It holds for a 2x2. We just don't really need to do it for 2x2 because it's so small. But we can pick any row or any column. So for this matrix here, we generally want to pick the row or column that has the most zeros, because that means that's the least math we'll have to do. So I'm going to pick this one right here, this column right here, because it doesn't matter what my cofactor is for 1, 1, or my cofactor is for 1, 2, or 2, 2, 1. Sorry, 2, 1. Because I'm multiplying it by 0. Okay, so now this one, cofactor for this number here. Remove the row, remove the column. Now I'm finding the determinant with these numbers. 2, negative 2, 1, negative 2, negative 3, 3, negative 1, 1, 2. I can draw my grid, plus, minus, plus, minus. I only really need my grid for the row I'm in. I'm on this number here, so it's going to be a plus in front. This determinant is going to be, once again, I can use cofactor expansion to do it. There's no zeros in this one, which is kind of annoying. But oh well. So it's going to be, I'll use row 1, 2 times -3, 3, 1, 2. So this is another way we can write it. 2 times that determinant minus -2 times this one, -2, 1, 1, 2. With those numbers. And then plus -1 times these numbers. So now I'm just squishing it all into one process. Here's one formula that essentially does that cofactor expansion. As you practice these problems, you will get more comfortable with identifying your cofactors. But for this one, cross out this row, this column. This is my remaining elements. Then my grid is plus, minus, plus, so I have this minus here. -2. Shoot. Undo that. Undo that. Go away. Cross out that one. These are my remaining elements. Then I have a plus here. This number, cross out those. These are my remaining elements. So I'm just doing the process all in one step. As you practice, that will be more comfortable for you. Okay, so calculating this, 2 times -6 minus 3 plus 2 times -4 minus 2 plus -1 times -6 minus or plus 3. And then you can keep calculating that through. So the bigger the matrix, the bigger the cofactors are, but you just follow the process through. So we got that one, we got that one, we got that one. Now we need this one. So 3, 4, 1. The sign in front is a negative, so I can write that right away. Remove the row, remove the column. 2, -2, 1, -2, -3, 0, -1, 1, -2. Once again, cofactor expansion. I'm going to pick this row. Generally, you choose rows. It's not necessary, but the convention is to typically choose a row. If a row doesn't have zeros or as many zeros, you choose a column like we did for this one. This column here has the most zeros, so why not use it? Okay, cofactor expansion. For my negative, or for my last column, or my last row, it's a plus, minus, plus. So I have a plus 1 times -2, -3, 1, -1, 1. So these 4. Then I have a minus 0. Woohoo! That's what I want. Plus -2 times 2, -2, -2, -3. And then just calculate that through. That is a very good question, Joey. Determinants do not exist for non-square matrices. So when we're talking about determinants, we are talking about a square matrix. That's it, period. There's no exception to the rule. So 1 times -2 minus 3 minus 2 times -6 minus 4. Okay, if I actually do this math, 2 times -9 plus 2 times -6 minus 1 times -3. So this first one here should be -27. Hopefully this works out. This one here is going to be -5 minus 2 times -10. 15. Okay, so here's my cofactors. The other two cofactors for this column in this big 4x4, I can zoom out, don't matter. Okay, so now I just do my final cofactor expansion calculation. So it's going to be, a determinant of A is going to be 0 times C11, but it doesn't matter. I don't care because I have my 0. Plus 0 times C21. Once again, I don't care what that is. Plus 1 times negative 27. Plus 1 times 15. Okay, my answer should be negative 40. Clearly it's not, which means I did something wrong. I feel like... Okay, so 0 times that, 0 times that. This is a plus. That plus is indicated there. That minus is indicated there. 2 times. This is why you show all your work. This is negative 9. This is negative 6. This is negative 3. This is negative 5. This is negative 10. So that one's right. Right? Basic, like it's just basic math. It's just addition and subtraction. And why is it always so confusing? My answer, according to MATLAB, should be negative 40. You can always check your answers with MATLAB. So let's go over to MATLAB. Just plug in your matrix. A equals 0, 2, negative 2, negative 1. 0, negative 2, negative 3, 1. 1, 1, 0, negative 2. 1, 1, 3, 2. So there's A. Determinant of A should be negative 40. You can always check your cofactors as well. Determinant of A, let's see, cofactor for my last one should be determinant of A, 1 to 3, column 1 to 3. My answer on my last one should be 10, not negative 15, which is weird. Maybe I wrote a number down wrong. Nope, I didn't. That's fun. C31. The 27 seems odd. Two times... Oh my goodness. Well, that's a 1. Sorry, zoomed in way too much. So it should be negative 5. That probably takes off a 2. So negative 25 here. And this last one should be negative 15? Yeah, this should be, no, this is 15. I feel like I'm missing a sign. My answer should be negative 40. MATLAB told me it's negative 40. So I feel like this should be a negative somewhere. Did I incorporate my negative? I did not. I forgot to negate the whole thing. Don't forget to negate the whole thing. So that's a negative 15. So this is negative 40. Okay, so review on that. Okay, so keep straight what you're calculating. So negative 25 is the determinant of this matrix. When you change the sign on your cofactor, you need to use your grid. So this is a positive negative 25. Okay, so that positive comes from, this outside positive comes from my cofactor grid for my 4x4. This positive, this negative, and this positive come from my cofactor grid for my 3x3. For this C41 here, down at the bottom, this positive, this negative, and this positive come from my 3x3 cofactor grid. But I have a negative from my 4x4 cofactor grid. So my overall answer is going to be a negative 15, or positive 15. Nope, I lied. My positive 15 is going to be a negative 15. I forgot I wrote that in. So once again, it's just basic math. There's just a lot of signs that you need to keep track of. Sometimes this notation here is pretty easy to follow. Sometimes that's pretty easy to follow because you only have a 3x3. But as you get bigger, don't be afraid to do separate calculations. So don't be afraid to do this all separately. Don't be afraid to write all of your cofactors out individually. Sometimes that's useful. Sometimes that's helpful that way. But notice, we got our negative 40. And this method is actually pretty straightforward. Once again, there's just a lot of things to keep track of, which is the case in any linear algebra problem. Okay, I just want to go over a couple more things. So for a 3x3, there is an alternative way to calculate the determinant. Specifically for a 3x3, it's I wouldn't call it a shortcut method. It's just different. So if I take this matrix and I copy it again. The alternative method for a 3x3 is calculated using the diagonals. I wrote this in the notes. It is right here. Here's the alternative method, specifically for a 3x3. Practically, it looks like this. Nope, wrong one. Practically, it looks like this. We essentially just write our matrix next to itself. And then we are going to multiply along diagonals. So this diagonal, this diagonal, this diagonal. So starting in our upper left, this diagonal is going to be 1 times 5 times 5. This diagonal is going to be 1 times 5 times negative 2. And this diagonal is going to be negative 4 times negative 4 times 5. What we do is we add all those numbers together. So here's my first set of diagonals. It's 25 minus 10. What's 16 times 5? 80. Plus 80. So this first set of diagonals gives me a number of 45. Nope, 95. That's a plus. Whoops. I was subtracting. On your exam, don't be afraid to just pull out your calculator because you'll have access to it for basic math. Don't try to wing it. So here's my first set of diagonals, and then I take my second set of diagonals. So essentially, you're going to do the same process, but going the other way. So starting with this corner, go the other way. So this first diagonal here is 1 times 5 times 5 plus this diagonal 1 times negative 4 times 5, and this diagonal, negative 4 times 5 times negative 2. And we add all those numbers up. So we get 25 again, minus 20, plus 40. Add all those together, we end up with 45. And then I take those two numbers and subtract them. I should get, oh, right. So it's kind of like our fish method for the 2x2. I take these diagonals and subtract these diagonals. So 95 minus 45 gives me 50. Which, inadvertently, is the same answer we got when we did cofactor expansion using column 2 and using row 1. So there's multiple ways to calculate a determinant. You can use cofactor expansion along any row or any column, and that works for any size matrix. For a 3x3, we can also use essentially the form of our fish method. I'm just coining it the fish method from here on out, the fish method. But now we have 3 diagonals and 3 diagonals. Add our first set of diagonals, our second set of diagonals, and subtract the 2 numbers. Use whichever one you're comfortable with. I like this method. The more I practice cofactor expansion, the more I'm comfortable with it. So sometimes I prefer cofactor expansion, especially if there are a lot of zeros. Sometimes I prefer this method if there's not a lot of zeros. Yes, so NotJev, this only works for 3x3s. You cannot do the diagonal method with a 4x4. The diagonal method does not work for a 4x4, only for 3x3s. On the final, typically, sometimes we might ask you to use a specific method, sometimes we won't. Typically for a determinant, we don't ask you to use a specific method. We might ask you to do, so on your homework, you're asked to find the determinant using cofactor expansion along a specific row or a specific column. So on your homework, you might be asked, use a specific row and do cofactor expansion along that row. On your exam, I'm going to try to leave it open for you to make sure that you can do whichever method you find most comfortable with. But you should know how to do all of this stuff. But like I said, I will have more ideas about what the final contains next week. But in general, I try to make it so that the final is as open as possible so that you have the freedom to choose what method you want to choose. Okay, so we are going to stop there because why not? On Wednesday, we are going to look at, just briefly, some determinant rules. So essentially, how does the determinant change as we change our matrix? And then we will solve a system of equations using the inverse and cofactors, which is the easier way, and Kramer's rule. Okay, so with that, I'm going to hop over to office hours. And if there are any final questions, I can answer them right now. I'm a little bit behind on the grading, but you will have all of your grades and everything finalized by this Friday. Oh my goodness. Royalty-free music, man. It's a winner. Okay. With that, have a nice day.